Hello everyone, I'm going to talk about my course project on magnetic resonance imaging. In my project I'm going to focus on the RF pulses and selective excitation. On the RF pulses side, I'm going to generate window sync pulses on MATLAB simulations with different time bandwidths, and I'm going to scale them to different flip angles as simulations on MATLAB. And also I'm going to talk about the spin-echo pulse sequences and why we need such kind of approach when we analyze the effect of transverse magnetization. And on the selective excitation side, I'm going to produce some sample scenarios like the ones in the textbook, and I'm going to simulate these scenarios, and I'm going to show the difference between selective and non-selective excitation, and I'm going to also explain how gradients are used in order to make the magnetization signal spatially selective. The frequency varying excitation is very fundamental in MRI, so it is most convenient to analyze different frequencies when the frequencies are gathered together as a rectangular function in Fourier domain. Therefore, the sync pulses are widely used in MRI since they transform into a rectangular function in Fourier domain. However, we know that the sync pulses are infinite functions, and it is impossible to generate perfect sync pulses at finite durations. Therefore, several windowing methods are used to minimize the effects of truncation in the sync pulses. In the MATLAB simulations, we worked on windowing sync pulses with different time bandwidths in Hamming window. In MRI, we use RF pulses with different flip angles to excite the spins. And in the following examples, I used 3 different flip angles, which were pi over 4, pi over 2, and pi, and I used these scaled RF pulses to excite the spins. And later on, I'm going to use these spins in order to explain the spin-echo sequences. In MRI, we mostly deal with magnetization of the transverse plane, and we know that we can use pi over 2 or higher degree RF excitation to generate such magnetization on transverse plane. However, when we use a single pi over 2 degree flip angle RF excitation, a signal which depends just on T2 occurs when we need a very fast scanner in order to analyze the signal, since the signal decays very quickly. So, Dr. Behman proposed a shrewd solution to this problem, and his solution underlies on the following analogy. A tortoise and a hare start racing. As the hare is very faster than the tortoise, it gets up front immediately. However, after some time, they're told to race back to the starting point, and we know that they're going to return to the starting point at the same time. In parallel with the analogy that the Dr. Han applied, another RF signal with flip angle degree of pi in order to rotate the precesses on the opposite direction. Just like the analogy that we mentioned, the precessing returns to the starting point in a time that is equal to the time interval between the first RF pulse and the second RF pulse. So in the simulation part, we assumed some initial conditions and generated the spin-echo sequence according to the model described above. We simulated the RF signals accordingly and plotted the magnetization vectors on the both transverse plane and the z-plane as given in the following results. On the selective excitation side of the project, we assumed 3 simple scenarios. And in the first scenario, we try to excite the spins with a non-selective excitation. In the second scenario, we try to excite the spins with a selective excitation, but with only a positive gradient. And in the third and the last scenario, we try to excite the spins with both positive and negative gradients, and the results are given as in the following.